Hi. So you've probably seen the thumbnail where the left image has more integration time and the right image has less integration time, yet the right image has about 3 times the SNR that the left image has. What is going on? Did the images use a different camera? No, same camera. Does one have a bigger aperture? Well, yes, one does have a bigger aperture. And it's the one that has 23 hours of integration time. So it still doesn't really make sense. What is going on? Well, the answer, I think, has to do with what detail is in astrophotography. And we'll get into that now. Welcome to Deep Sky Detail. All right, so what is detail in astrophotography? Well, I think it's a lot of things, but it can be boiled down to 2 main components. There's signal-to-noise ratio and there's resolution. Signal-to-noise ratio is basically just how much signal is in your image versus how much noise is in your image. And generally, we think that signal-to-noise ratio is affected by stacking. So if we stack multiple images together, we increase our signal-to-noise ratio. Resolution, on the other hand, is usually defined by arc seconds per pixel. So how much area of the sky is each pixel in your sensor imaging? Now, I've been accused on this channel of focusing too much on signal-to-noise ratio. However, I don't think I've ignored resolution. I've got a few videos that talk about all of this together, and even within my signal-to-noise ratio videos, I've generally poked fun at the fact that signal-to-noise ratio isn't everything. We pretended that a slingshot was our deep sky object, and you had a camera with only 1 pixel. It perfectly measures photons, and we're in space, so no light pollution. Let's take a look at the image from our camera, shall we? Here is the image from our 1 pixel camera. It's so beautiful. Look at that structure. What's that? A 1 pixel camera doesn't show any detail? Well, I like it anyway. Consider this example. If you have a 1 pixel camera and you have the highest signal-to-noise ratio that you can have, you're not going to have any detail at all. Likewise, if you have very high resolution, but you have no signal-to-noise ratio, you're also not going to get any detail. In astrophotography, sometimes we like to pick signal-to-noise ratio versus resolution. And while it's true that often we will trade SNR for resolution or vice versa, the fact of the matter is that both of them combine to give us detail. With that in mind, I thought I would make this very quick video comparing 2 images that I took of Messier 78 that have a lot of different types of detail in them. What is the answer to the question I posed at the beginning of the video? Why does the image on the right have so much more SNR than the image on the left? They're both taken with the same camera, under similar light pollution conditions, and of the same object, analyzing similar parts of the nebula. What's going on? Well, if you've been following this channel, you probably already have an answer. The image on the right was taken with a much faster setup. The image on the left was taken with my Ritchie Creation telescope. It has a focal length of about 1300 millimeters, and the primary mirror diameter is 150 millimeters. So it's an f9 scope. The image on the right, however, was taken with a new hyperbolic Newtonian that I just purchased. I'll be doing a full review on it eventually, and this is a preview of that. One of the reasons I bought it was because it is an f2.9 telescope. It has a smaller primary mirror than my Ritchie Creation, but the focal length is so much shorter and the f ratio is so much lower that in the same amount of time, it collects about 10 times as much light per pixel as my Ritchie Creation setup does. However, the trade-off is resolution. Instead of being sampled at about 0.7 arc seconds per pixel, I am sampling at over 2 arc seconds per pixel. So again, I'm trading resolution for signal-to-noise ratio. But is one of them more important for detail? I think it depends on how much time you have and how much light pollution is in your area. So let's take a look at both images and see how much detail is in a brighter region. When we zoom in, they actually look quite similar. The Ritchie creation has more resolution, the stars are a little bit tighter, and you can see a little bit of dark nebulae filaments emerging. It also looks a little bit less blocky, which is nice. The brighter areas are fine, but if we pay attention to the darker areas, I think there is actually more detail in the darker filaments in the hyperbolic Newtonian than in the Ritchie creation. If we look at a particular filament like this one, it's more pronounced in the hyperbolic Newtonian. If I eventually got 200 hours of data, or even 100 hours of data with my Ritchie creation, it would have higher resolution along with more detail, and it would probably be a better image overall. But at the moment, the SNR, in my opinion, provides more usable detail. This is especially visible with the Hilbert-Haro objects. When we zoom into this region and look at them, you can see filaments in the dark nebula spreading out in areas where hardly anything is showing up in the Ritchie creation. Of course, this isn't the whole story. Again, if we zoom into the Hilbert-Haro objects themselves, the hyperbolic Newtonian image is much more blocky and not as smooth as the Ritchie creation. So in terms of the brighter areas, the Ritchie creation is winning, in my opinion, while in terms of the darker areas, I think the hyperbolic Newtonian is winning. There is a secret to help you get more SNR with the Ritchie creation scope, and that's software binning. If I bin 4x4 on the stacked frame, it suddenly starts to look a lot like the hyperbolic Newtonian in terms of SNR. But now my resolution isn't really any better than the hyperbolic Newtonian. And there's also a secret to help you get more resolution with the hyperbolic Newtonian, and that's drizzling. But you will be sacrificing SNR if you do 2 times drizzle, for example. So there's no free lunch. I don't think the question is simply which is better, resolution or SNR. Even at high resolution, you need SNR. And even when you have a lot of SNR, you still need resolution. I think there's an interesting dynamic in which one you personally prefer. Do you like to sacrifice some SNR for resolution, or do you like to sacrifice resolution for more SNR? There are probably as many different views on this as there are astrophotographers. But I have a theory that if you deal with a significant amount of light pollution, you probably value SNR a little bit more than resolution, especially on your broadband targets. If you don't have much light pollution to deal with, you generally have high SNR anyway. Because light pollution noise is not as much of a problem, resolution may be more important to you. But that's just my opinion. Maybe you have different thoughts. If so, let me know in the comments. If you'd like a deeper dive into how signal is affected by focal length, aperture, and pixel size, check out my video on the Triforce of Astrophotography. Thanks for watching.